On the Earth, hydrogen only exists as a diatomic molecule called dihydrogen or in a combined form. This most abundant element accounts for approximately 70% of the mass of the universe. In its combined form, besides water, hydrogen occurs in plant and animal tissues as carbohydrates and many other compounds like hydrocarbons. It is, therefore, the third most abundant element on Earth, constituting 15.4% of its crust and the oceans. Hydrogen with atomic number 1 has 3 isotopes: protium, deuterium, and tritium. It is the only element whose isotopes are named. Protium has no neutrons. Deuterium has 1 neutron, while tritium has 2. Among the 3, protium, with a concentration of 99.98%, is the most abundant. The concentration of deuterium is only 0.0156%, mostly in the form of hydrogen-deuterium molecules. The concentration of tritium is about 1 atom per 10 raised to the power 18 atoms of protium. It is the only hydrogen isotope that is radioactive and emits low-energy beta particles. Because of its atomic number 1, hydrogen is the first element in the periodic table. However, its position in the periodic table is debated because of its resemblance to both alkali metals and halogens, as well as because of its unique behavior. Let us see how hydrogen is similar to alkali metals, yet different from the group at the same time. Its electronic configuration is 1s1. Therefore, like the alkali metals, lithium, sodium, and potassium, hydrogen also has only 1 electron in its outermost shell. Due to this, these elements possess similar electropositive character, allowing them to readily lose an electron to form positive ions. Thus, similar to alkali metals, hydrogen also shows an oxidation state of +1. For example, in hydrochloric acid, hydrogen has an oxidation state of +1, which is similar to that of alkali metals such as sodium and potassium, in sodium chloride and potassium chloride respectively. Like alkali metals, hydrogen acts as a strong reducing agent. For example, it reduces iron 3 oxide to iron, which is similar to the behavior of the alkali metal potassium in its reaction with boron oxide, wherein it reduces boron oxide to boron. Though hydrogen is similar to alkali metals in several aspects, it also exhibits certain properties that are different from alkali metals. For example, the ionization energy of hydrogen is very high as compared to alkali metals. It shows non-metallic behavior, unlike alkali metals. It exists as a diatomic molecule in the form of a gas, whereas alkali metals are solid and exist as monoatomic molecules. Hydrogen mostly forms covalent bonds, whereas alkali metals form ionic bonds. For example, HCl is covalent, whereas NaCl is ionic. Let us now see how hydrogen is similar to halogens, and yet different from the group at the same time. Like halogens, hydrogen has only one electron less than the nearest noble gas configuration. For example, it needs one electron to attain the noble gas configuration of helium. This is similar to halogens, which have an outermost shell configuration of Ns2, Np5 and need just one electron to attain noble gas configuration. The ionization enthalpy of hydrogen, 1312 kilojoules per mole, is very close to that of halogens like chlorine, 1255 kilojoules per mole. The oxidization state of hydrogen, -1, is similar to halogens in some of its compounds. For example, in sodium hydride, hydrogen has an oxidation state of -1, which is the same as that of chlorine in sodium chloride. The molecules of hydrogen and halogens are diatomic. Like halogens, hydrogen is non-metallic in nature and usually exists in gaseous form. In spite of several similarities with halogens, hydrogen also exhibits behavior that makes it different from the halogens. For example, unlike halogens, hydrogen has less tendency to take up an electron to form a hydride ion, whereas halogens form halide ions very easily. In a hydrogen molecule, atoms do not possess any unshared electron pairs, whereas in halogen molecules, every atom has 3 pairs of unshared electrons. The oxides of halogens, such as chlorine oxide, are acidic in nature, whereas hydrogen oxide or H2O is neutral. Because of this unique behavior of hydrogen, it is placed separately in the periodic table. This uniqueness of hydrogen makes it an industrially important element. Now, let's look at the ways to prepare dihydrogen both in the laboratory and industrially. In the laboratory, the most common way of preparing hydrogen is by the reaction of granulated zinc with dilute hydrochloric acid. The setup consists of granulated zinc in a conical flask fitted with a thistle funnel. In this flask, dilute hydrochloric acid is poured drop by drop through the thistle funnel. As dilute hydrochloric acid reacts with the zinc granules, hydrogen gas is released. The gas is collected by the downward displacement of water. Sometimes, the reaction stops midway as the bubbles of hydrogen gas stick to the surface of the zinc granules, preventing its further reaction with the acid. To avoid this, a few crystals of copper sulfate are added to the reaction mixture. Another common method of preparing hydrogen in the laboratory is by the action of metals like zinc and aluminium on strong alkalis like sodium hydroxide and potassium hydroxide. For example, zinc reacts with sodium hydroxide to give sodium zincate and hydrogen. Commercially, hydrogen is prepared by the electrolysis of water using platinum electrodes. Sulfuric acid is used to acidify water, making it a better conductor of electricity. When an electric current is passed through the water, it decomposes into hydrogen and oxygen. Hydrogen gas is liberated at the cathode and oxygen at the anode. The volume of hydrogen formed is double that of oxygen. Another industrial method of dihydrogen preparation is by passing steam over hydrocarbons or red-hot coke at high temperature in the presence of a catalyst, like nickel. The product contains carbon monoxide along with hydrogen. The number of moles of hydrogen and carbon monoxide produced depends on the hydrocarbon. For example, 1 mole of methane produces 1 mole of carbon monoxide and 3 moles of hydrogen. The mixture of hydrogen and carbon monoxide is called water gas. Water gas is further used for the synthesis of methanol and a number of other hydrocarbons, as it produces a lot of heat when burnt. Hence, water gas is also called synthesis gas or syngas. Syngas is also produced from sewage, sawdust, scrap wood, waste paper, etc. When syngas is obtained by the reaction of steam on coal, the process is known as coal gasification. It is difficult to separate dihydrogen from syngas. Therefore, the production of dihydrogen is increased by reacting the syngas with steam in the presence of iron chromate as a catalyst. The reaction produces mixture of carbon dioxide and dihydrogen. The carbon dioxide produced is removed from the mixture by scrubbing with sodium arsenite solution. This reaction is known as water-gas shift reaction. Currently, almost 77% of hydrogen required by the industry is obtained from petrochemicals, 18% from coal, 4% from the electrolysis of aqueous solution, and 1% from other sources.